to this week's string seminar, and this is also a joint seminar with the Maths Physics seminar series. We are pleased to have Professor Ramadas from CMI, and he's going to talk about symplectic lattice theory and SU2 character varieties. Over to you.
Okay. Thanks. Thanks for coming. Thanks to Spenta and Rajesh for inviting me to give this talk. And again, thanks for coming and thank you. So I want to introduce an approach to the integrals that occur in SU2 lattice case theory, and try to convince you that this approach might be fruitful. I call this symplectic lattice theory, and it's by connecting the integrals of lattice case theory to what are called SU2 character varieties by mathematicians, and which are familiar to physicists as the phase space of SU2 Chern-Simons theory. Okay, so I will say a little bit more about that later. Okay, so this is the overview. So there's a fair bit of ground to cover, so I will go quickly, but please stop me. But I will be working on the board also. That will maybe slow me down a bit. So I'll give you a minute to look at the topics that we have to cover, and let's launch into the talk. So I start with perhaps the part that may be least familiar to many of you, and which is my kind of comfort zone, which is the symplectic geometry of the SU2 character variety. So let sigma be a compact. So for those who get worried by the abstraction and excessive geometry, this is the easy part. It's really soft. I mean, we will get to the meat of the matter a bit later. So let this be a compact, orientable, and without boundary surface of genus. For many reasons, it's useful to assume that the genus is at least 2. So this will be a kind of running example that we will do for much of the talk. There'll be more interesting and physically relevant examples later. So let me. So this is I hope you see a surface with which is a donut, but there are 6 holes in it. So this is a surface sigma, and its genus is 7. Okay, this will be a kind of our running example. We will decorate this in many ways later. We take the space of SU2 gauge fields on this surface, but not all SU2 gauge fields, but we want the curvature to vanish. So they're called flat gauge fields. We let the group of SU2 gauge transformations act on this. And when you do this, you get a space, a manifold with some very mild singularities. This is the phase space of SU2 Chern-Simons theory on the space-time, which you get by taking sigma and crossing it with R. So, and it's known that, so this is why it's called the phase space, that it's a symplectic manifold. It has a symplectic structure. It's one of the natural examples of a phase space which is not the cotangent bundle of a configuration space. And it has dimension twice 3g minus 1, where g is the genus of your surface. So in this case, this would be twice 3 into 6. Which is 36, right? Yeah. So these are called character varieties by mathematicians because they can also be realize, I mean, there is a fairly natural isomorphism of this with representations of the fundamental group of the surface into SU2 modulo the adjoint action of the group SU2. And in that avatar, it's a sort of real algebraic variety, and hence the term character varieties. Okay. Sorry?
The fixed
Yeah, from the, yeah, there are the, if the connection can be reduced to a U1 connection, then the action is not free and you get singularities. Yeah. But they are very low dimensional and we can ignore them. So the simplex structure is well defined up to a non-zero overall constant and defines, each symplectic structure defines a Liouville measure. You can normalize the Liouville measure so that the total volume is 1. So we can pretend that you're doing probability theory. So now let C tilde be a closed loop in sigma. So this is my sigma here. So let C tilde be a closed loop like this. Okay, it's not an oriented loop, it's just a closed circle. Yeah. So now, given a flat connection, you can take the parallel transport around the loop, and so that will give an element of SU2, but it's well defined only up to conjugacy. But if you take the trace of that, it's well defined, it's gauge invariant. And you can write it as, because the group element will be isomorphic, will be conjugate to an element of the kind e to the I theta, it is the minus I theta. The trace of that will be twice cos of an angle. And you can write this in this form. So you get this function which associates to every gauge field a real number in the range 0, 1. Okay, there is some non-uniqueness when the holonomy is -1, and that you don't care because again that happens on a sort of very small set. Okay, so we will just somehow arrange that this function takes values in 0, -1, open interval 0, -1. Okay. So there are reasons why you deal with this normalized function rather than the trace itself. Okay, which let's deal with this. Now, suppose given L loops, C1 tilde, CL tilde, yeah. Then for each of them, I get this function. And clearly, it's not interesting to consider a contractible loop because then the holonomy will be identity and the trace will be just constant. Okay. So we assume that each loop is non-contractible. And if two loops are homotopic to each other, they give the same function. So we assume that the loops are mutually indifferent homotopy classes. And then it is a fact that you cannot have too many of such loops. You can have at most 3 times G-1 such loops. And if you have strictly less than 3 times G-1, you can add some more loops to make it a full set. Okay? Not in a unique way. If you do this, you get what's called a Pan's decomposition of the surface. So let me illustrate that here. So here is a Pan's decomposition. I hope I get this right. Yeah. So in this case, I should get 18 loops, and I hope because there are 6 of these whole things, and each of them there are 3 of these loops, so there are indeed 18 loops here. Okay. So no, there are there no. I don't include homologically trivial loops. No. I don't know. Okay, let me not say anything.
Normally, it can come A cycles.
Yes. Yeah. Oh, you mean some? You mean these are not homologically independent? These are not homologically independent. No, because you can have at most, the A cycles and B cycles will give you 2 G1s. Yeah, so these are more than those. So they are not homologically, they cannot be homologically independent. Yeah. So now we can associate to any such Pan's decomposition what's called its Trinion graph. It's a trivalent graph. The vertices correspond to one of these pairs of pans. So by the way, so you notice that these divide the surface into these what are called panthalon by the French, or pairs of pans by the English, I guess. So for each of the pairs of pans, you have a vertex. So and you join two vertices if the corresponding pairs of pans share a common boundary. So in this case, the Trinion graph will look like this. Yeah. Please help me here. I think I'm okay here. Okay, so you get a trivalent graph called the Trinion graph of the Pan's decomposition, and conversely, the Trinion graph encodes the surface and the Pan's decomposition in a fairly obvious way. So, okay, so there is a dictionary between trivalent graphs and Pan's surfaces together with Pan's decompositions. So we will only consider Pan's decomposition such that the Trinion graph has no loops, meaning an edge going from a vertex to itself, and such that it cannot be disconnected by cutting one edge. In other words, we don't allow such decompositions of the surface. Some junk here, and a circle here, and we don't consider decompositions of this kind either, because this will correspond to a Trinion graph which can be disconnected by cutting this edge, and this will correspond to a Trinion graph like this. So we don't, for some slightly annoying reason, we don't allow such Pan's decompositions. Okay. That's just a legal statement that I'm making now. So now, supposing I'm given a Pan's decomposition of a surface. So as I said, that will give you 3 times G-1 disjoint circles. And for each of them, I can take the trace of the holonomy. That will give me a 2 cos theta, write that theta in terms of pi times a t. So I get a function with values in 0, pi. So there are 3 times G-1 such functions. Put them together into a vector like that. So I get a map into 0, 1 into 3 raised to G-1. So then by the works of people listed above, Goldman and Jeffrey-Weitsman, this, the following things hold. The closure of the image of this map T is an explicitly described polytope in R to the 3G-1, which is in fact contained in this hypercube. I will come to the description of this polytope later. Secondly, so this is a situation, I have this map from A of mod G, which I call T, to R to the 3G-1. Here I have the Liouville measure here coming from the symplectic form. Look at what it's called. So I will say this in fancy language, but I explain what that means in the red sentence. If you take the push forward of this measure here, the Liouville measure here, by this map, it is actually the Lebesgue measure on this R to the whatever times the indicator function of the polytope P. Okay. What does that mean? That means that if I take any function here, any real valued function f here into R, and pull it back by this map to the space AF mod G, and integrate against the Liouville volume element on the character variety. That's the same thing as taking this function, restricting it to the polytope and integrating it there. So that is so why have I put Duistermaat-Heckman within brackets here? So this is a famous theorem of these two gentlemen, which says if you have a compact symplectic manifold and a symplectic action of a torus of half the dimension, then if you look at the moment map, then the push forward of the Liouville measure has this property. There is the image is actually the image by the moment map is actually a very explicitly described polytope, and the image of the measure is just the Lebesgue measure restricted to the polytope. So this is the so-called Duistermaat-Heckman theorem, which doesn't quite apply here because of the singularities of AF mod G. But nonetheless, because of Goldman's work and Jeffrey-Weitsman's work, you can fix things so that in fact the consequences are still true. And this is the result that we hope to leverage to say something interesting about lattice gauge theory integrals. So this is, since the result is somewhat crucial, is the statement clear? I mean, it's abstract, but I mean, it is actually quite neat and simple. So let me repeat. You have on this phase space n functions, okay? And I forgot a very important statement. A function on a symplectic manifold defines a vector field, and between functions you can define Poisson brackets. The point is that because so if I take two loops on the surface and look at the corresponding Wilson loops, the corresponding functions on phase space Poisson commute. Okay, so these 3G minus 3 functions define mutually commuting vector fields. These vector fields generate actions of S1. So you have an action of S1 to the 3G minus 3 on the phase space, which is symplectic. And this map is just the orbit map for that action. Okay, so that is the generality in which you should think of the Duistermaat-Heckman theorem. Okay, so by omitting this crucial remark, I'm afraid this was expositorily not forgivable. I'm sorry. But having made this remark, are there any questions? Can I go on? Yeah. So let me parse this equation just because it's so important. I take a function of the 3G minus, there should be a bracket here, 3G minus 3 variables, restrict to the polytope. This 1p means just restricting to the polytope, integrate that in R to the 3G minus 1. That is the same thing as taking the corresponding function of the flat gauge field and integrating against the Liouville volume element on the phase space. So now here is the description of the polytope. So so as I said, it's a polytope and it's given by a certain number of inequalities. And what are the inequalities? Take any vertex of the Trinion graph. Remember, a vertex of the Trinion graph corresponds to one of these pairs of pans. The three edges correspond to these circles. So here is the vertex. There are three circles here. So, and each of them will have a corresponding function t. So let me call the functions t1, t2, t3. So then the values of these functions on the space AF mod G are constrained exactly like that. Each of them has values between 0 and 1. That is nothing. That is by design. But the sum must be less than or equal to 2. And you have that kind of inequality. So these are precisely the conditions that T1, T2, T3 form up to some normalization the sides of a spherical triangle. Okay, just to aid some understanding. So you have this constraint for every vertex. And the polytope is given by the intersection of these constraints. Now, what makes the integral over the polytope tractable is that each of those constraints can be very efficiently implemented. So take the three-dimensional polytope given by that equation up there. So, and take the indicator function of that polytope. So in the T1, T2, T2, T3 hypercube, I have a polytope contained here. I'm not very good at drawing that polytope. It will look something like this. So I've called that P3. And take the indicator function of that polytope, namely the function which is 1 inside and 0 outside. That function in L2 of this hypercube, 3 cube, has this sign expansion of this kind. This is the identity that makes computations tractable. And once this identity is shown to you, it is not difficult to, derive, but the most efficient derivation is done using some analogy with the well-ended algebra for SU2. I leave that as a sort of teaser. Okay, so now having said all, yeah.
Explicit formula for the indicator function. Did that somehow depend crucially on the particular the spherical triangle inequalities?
No. Once the description is given, you can just you can derive
any polytope inside.
No. This polytope.
This particular polytope.
This polytope. Otherwise, of course, I don't know of any inequality of a expansion.
Are there other special polytopes?
Not that I'm aware of, but I'm not an expert on polytopes. Okay, this is the only polytope I know about.
Thank you.
Yeah. So now let us, yeah.
This Duistermaat-Heckman also has this fixed point theorem, right? I mean the localization. Is there some special case of this?
In fact, the vertices of the polytope are the images of the fixed points.
I see. Yeah. Okay. Thank you.
Yeah. Okay. So now with all this, in fact, let's do some board work. Let us compute the distribution of one Wilson loop. Because as I said, now that we've normalized the Liouville measure to have probability total volume 1, we can pretend we are doing probability and talk about distributions of variables. So for example, here, if you do this, remember I had drawn the Trinion graph like this. There are 6 of these bubbles, okay? And each of these has a variable Ti attached to the edges. So so I take this loop C tilde. I'm interested in the distribution of values of the corresponding Wilson loop. So take any function of that Wilson loop. So take any function, let f be any function continuous on 0, 1. And let's consider integral f of w c tilde a d mu l. Okay. So this, so I take the normalized Liouville measure, total volume 1, take this function of the Wilson loop and integrate it over AF mod G. And if I know this for every function f, I know how the values of the Wilson loop are distributed. Okay. So now, by what we said before, this is equal to integral over the polytope. So we can assume that we take C tilde, which is just one loop, and add more loops. So you get 3G minus 3 loops. So and we will assume that this is actually C tilde 1 in that large collection. So then this will be f of essentially T1 over the polytope. Okay, and then this integral over the polytope, you can put in all these, sorry. This identity everywhere. So note that this will involve an introduction of an integer n for every one of these vertices, because for every one of those vertices, there is a constraint. Right? And when you, so what you get will be things like this. So there'll be N1, N2, and then you will have UN1 TA, UN2 TA, where TA is this variable. And when you integrate over TA, you will get a delta function N1 equal to N2 because of the orthogonality of the UNs. So all the N's get identified around the loop. So the upshot is that you get this thing equal to integral f of t, just believe me, √2 over pi 2g minus 1 to sine squared t dt divided by √2 over pi twice g minus 1 twice sine squared t dt. This is just normalizing the total volume to be 1. This corresponds to the fact that the Liouville volume has been normalized to 1. So now if you see what happens as G becomes very large, yeah, I mean, so this is in the limit G becoming very large. I'm sorry, I have not prepared this well. So essentially, this goes away and you get this. This is in the G going to large limit. So if you see what this is happening, it shows that the distribution of one Wilson loop is becoming the standard distribution on the circle induced from SU2, the invariant integration of an invariant function on SU2 as a function on the torus. So this is really the measure on the torus of SU2. Okay, so I really haven't prepared this computation well. Let me go ahead. So my point is that this is an effective way of computing how Wilson loops behave in the with respect to the symplectic side. Okay. Now, in fact, you can do two Wilson loops, and you can see what is their joint distribution. It turns out that the joint distribution for finite G is not a product, but as the G goes to infinity, the joint distribution becomes a product distribution and the product of these. So in other words, Wilson loops in the limit of large genus become independent variables. Each of them have this distribution. Okay, so keep that in mind. So now, how to go from graphs to associated surfaces? So because after all, I'm interested in lattice gauge theories, and lattice gauge theories are defined on graphs. So let lambda be a finite connected graph, which we will refer to as a lattice, because eventually we'll be interested in lattices with V vertices and E edges. Its first Betti number is given by that expression, where now we will suppose, as I said, that B is at least greater than or equal to 2. Now, suppose that a set P of closed loops in lambda is given. So here, this is the simple example of a lambda, and I'm given two loops, which I'm shown displaced from the graph itself for clarity. These are the two red loops, and I'm calling them plaquettes. Now, one associates to lambda something called a three-manifold of a type called a handle body as follows. Embed lambda in any three-manifold and take M lambda to be a closed regular neighborhood, a small enough neighborhood of the graph. And you get what's called a handle body, a certain type of three-manifold called a handle body. It's not important for us what that means. Okay. Now the graph sits inside this three-manifold as what is it called its spine. So the spine here is shown in black. The three-manifold is the body of this thing, and its boundary is a surface sigma, which depends on lambda. Now the genus of that surface is actually the Betti number of lambda. In this case, the genus is 2. So this picture is what you should keep in mind. Now, suppose there exists a judicially chosen set of 3G minus 1 closed loops in sigma that give a Pan's decomposition, and a subset of these loops that I forgot to highlight. It's highlighted in red there. That is an important fact. This lambda sits inside the three-manifold as its spine, and there is an inward map from the three-manifold to the spine called, which is a retraction. In particular, there is a map from the boundary surface to the spine. We will make use of it. So suppose there exists a set of 3G minus 3 closed loops in the boundary that give a Pan's decomposition, and a subset of these loops such that their retraction from the boundary to the spine gives your set of plaquettes that we saw before. Okay, so remember, so this is the two plaquettes that I had in the graph, the thickened guy, and now on the boundary I've drawn 3 loops. There are 3 loops in red. 2 of them under the when I retract to the spine will give the two plaquettes that we had seen before. But there's a third one, because this is genus 2. I need 3 loops to get a Pan's decomposition. Okay, so in fact, in this case, what I wanted you to suppose is possible, and I have illustrated that. Okay. Now, this is the Trinion graph of our toy example. So if you look at these 3 loops on the surface, they decompose the surface into 2 pairs of Pans, and this is the Trinion graph that you have. Okay, so this is the main point of the talk, and so our hope and conjecture, backed up by some evidence, some of which I presented when I talked about the distribution of 1 Wilson loop and then the 2 Wilson loops, is that in the limit of large lambda, integration over the character variety with respect to the Liouville measure approximates lattice gauge theoretic integrals. Slightly more precisely, supposing I'm given a function of 3G minus 3 variables, real variables, you can, on the one hand, consider the symplectic integrals, which we have talked about before, take the corresponding function of the holonomies of flat connections, integrate against the Liouville measure. Okay, and we know how to evaluate those in terms of the Duistermaat-Heckman formalism. The claim or hope or conjecture is that these approximate the corresponding lattice integrals, where remember that the difference between the first line and the second is that in the first line I have C tilde, and in the second line I have C. The C tildes are curves on the surface. The C's are curves that I get in the lattice, closed curves I get in the lattice by retracting the closed curves from the surface to the lattice. And
Sorry,
here,
what is dimension of the lattice? Dimension of the lattice. What is it? What is dimension? Lattice, dimension.
I can't hear you.
Yeah?
What
is lattice dimension, I say?
What do you mean by dimension?
Lattice dimension.
I'm sorry, I don't follow.
Lattice. It's a lattice in what dimensional space? Lattice.
No, we will come to sort of actual physical. I don't know where to look. We'll come to actual physical lattices in a minute. Please be. Yeah, thanks for the question. We will come to the yeah. So far we were looking at toy things. Yeah. Now, before I go on to the toy things, I should say that in addition to distribution of individual Wilson loops also obey constraints between them. For example, there are non-abelian Gauss's law. If I take a cube in 3 dimensions and take a 3-dimensional lattice, and if I take a unit cube, there are 6 holonomies corresponding to the 6 faces, and they are not independent. They have constraints between them on the lattice. So these imply things for integrals. So when I multiply these 6 holonomies against characters of the corresponding, against 6 characters and integrate, do a lattice integral, there are constraints. And you can ask, are these constraints reflected on the symplectic side? Again, it's interesting computation. You can check that on the symplectic side, you do recover these constraints in the large lattice limit. Okay, I don't have time to illustrate, to derive this, but you can check this. So now back to your question, let's consider a physically interesting example. Let's consider physically relevant lattice gauge theories. So if D is the dimension of space-time, in this, we will mostly be concerned with D equal to 3. By a lattice, we mean the graph constructed as follows. First, we construct the infinite graph with vertices with integer coordinates and edges going from each vertex to its 2D nearest neighbors. Let L be a positive integer and identify vertices if each coordinate they differ by a multiple of L. So in other words, you make the lattice periodic. So you get a periodic lattice. So now there are L to the D vertices and DL to the D edges. So the Betti number is given by that formula. A plaquette, we all know what a plaquette is in this case. These are the closed loops around the faces of unit cubes. Now, some numerology, if D is 3, there are 3L cube plaquettes. The genus of the associated surface is 2L cube minus 1. And the Pan's decomposition of the surface will have 6L cube loops. So the plaquette, so if you manage to lift the plaquettes to the surface, in other words, if you manage to find closed loops on the surface that under the retraction go to these plaquettes, we will need to find 3L cube more loops to get a Pan's decomposition. So, I mean, this is a quick reminder of what are the integrals we are interested in lattice gauge theories. Since for this audience, I don't need to spend time on that. I will just pass over that. So in D equal to 3, the lattice looks like this. I have drawn 2 plaquettes in red here. Now, if you pump up the lattice, this is what the regular neighborhood of the lattice looks like. So you can think of this as sitting inside a 3-dimensional torus. So the opposite sides are identified periodically. And the boundary of this three manifold is the corresponding surface. And you can see, hopefully, let me see if I can. So there is a red loop here, and you should see another red loop here, which project to these 2 red loops under the retraction. Okay. And of course, there are many more plaquettes, and each of them will correspond to a loop on the surface. And so this way, you will get 3L cube loops on the surface. But for a Pan's decomposition, I need to find 3L cube more loops. Now, the way to visualize this is to think of the dual lattice and take a regular neighborhood of the dual lattice. And then if you look locally around a vertex of the dual lattice, remember a vertex of the dual lattice corresponds to the center of one of these cubes here. Locally around one of the vertices of the dual lattice, if I look at the same surface now as a boundary of a tubular neighborhood of the dual lattice, after some shrinking, it will look like this. And the 6 plaquettes that we had earlier around at the 6 faces of a cube here will be the 6 red loops here. Remember, but I need for every vertex, I need 3 more loops. And those are the loops in blue, which now together give a local Pan's decomposition here, and globally they give a Pan's decomposition of the surface. So this is the Pan's decomposition that we will work with for the 3-dimensional lattice gauge theory. When you do that, the corresponding Trinion graph looks like this. The red long lines correspond to the plaquettes that we saw before. The blue lines correspond to the additional 3 circles that are needed for the complete Pan's decomposition. So this is the Trinion graph that you get. And if the blue edges are contracted, we get a copy of the dual lattice of lambda. I mean, so I'm going fast here and I have some time. And this, since this is kind of crucial, let me ask at this point. Is everybody sort of struggling with me? I mean, you see what I'm, so I have explained the general philosophy. The philosophy is that you take a finite graph, embed it in some 3-manifold, take a regular neighborhood that gives you a 3-manifold with boundary, which is a surface. Find closed loops on the boundary that under the retraction go to the plaquettes that you are interested in. Eventually they will be part of some, they will define some action. Okay. There is a pious hope that the integrals of the corresponding functionals over the Chern-Simons symplectic phase space for the surface in some way approximate the corresponding integrals for the lattice theory for the graph. There is a bunch of evidence for that. Now, armed with that evidence, or I'm now considering the specific case of a 3-dimensional periodic lattice. Let me repeat, start with the 3-dimensional periodic lattice. For each cube, there will be six of these plaquettes shared between 2 cubes, each shared between 2 cubes. So there will be 3 L cubed. If L is the number of sites, the site length, the periodicity in each direction, there are L cubed vertices. There are 3 L cubed plaquettes. This is the corresponding 3-manifold, the boundary is the surface. You will get 3 L cubed obvious closed loops which are disjoint on the surface, which retract to the plaquettes. Add 3 L cubed more loops to get a Pan's decomposition, and that is shown here. This is the corresponding Trinion decomposition. Each vertex corresponds to a pair of Pans. The edges correspond to shared circles. And now, okay, here is the, and if the blue edges are contracted, remember the 3 blue edges all lie on this sphere, and the sphere corresponds to a vertex. This is a sphere around a vertex of the dual lattice. So the 3 edges are contracted, that they contract to the center of the sphere, which is the vertex of the dual lattice. So this is why this is the dual lattice of lambda. So now you put all this into your machine and do the Duistermaat-Heckman formula, replace, leave aside whether this has anything to do with the lattice gauge theory that you're interested in, but see what Duistermaat-Heckman give you for the partition function of the lattice gauge theory with Wilson action, except that instead of integrating over lattice gauge variables, I integrate over the AF mod G. And then, but I use Duistermaat-Heckman. I use my expression for the characteristic function of these three-dimensional polytopes. And you get this expression for the symplectic partition function. So now, what does this correspond to? So let us parse this expression. Here, okay, so let me guide you through this expression. This is just the partition function. For every vertex of the dual graph, so V gamma is a set of vertices of the dual graph. You have an integer that runs from 0 to infinity. You have this factor. So if I fix one set of integers, so you can think of this as, so assignation of an integer to every vertex of the dual graph is a configuration for this dual theory. Given an assignation of integers, there is this factor, which is a product over all vertices of the dual graph. And then there is a factor which is a product of factors for every edge of the dual graph. Given an edge of the dual graph, it goes between two vertices of the dual graph, which I call V1 and V2. At each of those vertices, I already have my configuration has a integer nv1 and nv2. Okay. And this sum runs over the different absolute value of the difference of these integers at the two ends and the sum. And the tilde means that you omit every alternate term in the sum. And then there is this expression where it's kind of complicated. And by the way, E is the coupling constant that we saw several slides ago, which in the slide I skipped over, saying you know that is a Wilson action. And these integers n are multiplicity related integers. They have to do with representation theory of SL2, and they are non-negative also. So this whole thing is a partition function for some other model, which has the merit that it's a sum of positive terms. So that should be of some use if you want to prove anything rigorous about this. Just one second. Right.
I mean, you first fix the vortex and then you have sum over NV, right?
So first we fix for each NV runs from 0 to infinity. So that is a multiple sum. The first sum is this sum is a multiple sum for every.
So that's why I'm saying it should be exchange probably, right? Yeah.
So that should be, I mean, meaning these two, this is for every V. So there should be two summation. So this should be a summation for every V. This is a different V. Yeah.
Okay.
Thank you.
Okay.
Yeah. So that should be a V prime. Yeah. Thank you. Yeah. So now you can do something else. Supposing I have a plaquette correlations. Remember, a plaquette corresponds to an edge. So all that would happen is that for two edges, and edges correspond to these variables t. For two of the variables t, you stick in some function into your Duistermaat-Heckman formalism and do this thing, and you get another expression which is also quite explicit. I have not reproduced it in this lecture. You can, if you, instead of taking the Wilson action, you take the Migdal action, it's an altogether more pleasant expression that you get here. I don't know if the Migdal action is used except in 2 dimensions, but you do get a pleasant expression. You can take the Tohoff loop expectation and again get expressions. In all cases, they are, okay, so I'm winding up. In 2 dimensions, we can do this and you can actually evaluate everything explicitly and you get standard expressions. I myself consulted the old paper of Gross and Witten, and right at the beginning they do the case of SL2, and you get exactly the same expression in the large lattice limit. Now in D = 4, there are some topological issues sorted out. this hope that plaquettes can be lifted to non-intersecting loops on the associated surface fails in the case of 4 dimensions. So if you take the plaquettes in the case of 4 dimensions, there are too many of them to be lifted to the surface in a way that they are mutually non-intersecting. So I may have to, but as I understand it, it's not kind of absolutely God-given that you should take all plaquettes. In the lattice gauge theory, you can kind of thin out the plaquettes a little bit without hopefully changing the universality class. I'm hopeful that something like that may work. So after thinning out plaquettes, I can lift it. I've not worked this through. More interesting is what happens if you introduce complex structure on the surface. Is there a way one can use that to have something that looks like a lattice fermion? That looks promising. I have some ideas. The numerology looks promising, but I have not worked this through. Okay, I have, as I feared, I've gone too fast and come to the end of my slides, but yeah, such as it is. Yeah, thank you.
Any questions for Professor Ramadas?
Sorry, can't you comment again? What is the limit? What is the result of the limit G tends to infinity? You have an integral, but what happened when G tends to infinity?
This corresponds to the limit L going to infinity, because L and G are closely related. As the size of the lattice goes to infinity, the genus goes to infinity. So it's a thermodynamic limit.
Thank you.
So when you say that you are approximating, I mean, you expect that this is an approximation, right?
No, I mean, the point is, I hope that in the thermodynamic limit, the two things coincide. So if you, in other words, if you, for example, if you take the plaquette correlations for this model and prove that they have exponential decay, that can hopefully be leveraged to give exponential decay of correlations for the lattice model.
I see.
Yeah, because so unless there are some subtleties to see, what is clear is that if you look at finitely many Wilson loops and their joint distributions, and including constraints between them, they are replicated in the limit. I mean, at least to the extent that I have checked them. That is, and these are non-trivial computations. So I mean, at least Gaussian certain things. So I believe that if I take finitely many loops and look at their correlations, they will converge to the lattice limit in the thermodynamic theorem. Unfortunately, the action involves sums over all plaquettes. So there will be a delicate question whether this convergence is strong enough to control the things that you need to do. But modulo this analytical control, I mean, the first thing to do is to check whether with these symplectic partition functions or symplectic correlation functions, one has interesting phenomena. In fact, the first thing is to check if at the high temperature limit, at least you get exponential decay. In fact, I was discussing with Rizapridhim that, and if one has such phenomena happening with these expressions, then one can do the sort of, I think it might be hard, but somewhat less interesting work of proving that that is I mean, is it clear? Yeah. See, finitely many Wilson loops, I have really no doubt that they have the same joint distributions. I mean, the point is that, so when you're only looking at Wilson loops, so at finite temperature, it is the distribution of Wilson loops dressed by the action. That's of interest. So in other words, think of the Wilson loop, the values of the Wilson loops as having some measure. If those measures agree, then if you put in some functions, Yeah.
So hello, hi Ramadas. Yeah.
So is this Rajesh?
Yeah. Hi.
Yeah.
No, as we discussed that day when you also explained to me, so this is in a way a way to to write things in terms of the individual plaquette holonomies, the probability measure.
Right.
And approximating it over the individual plaquette holonomies. But I was thinking in the thermodynamic limit, what that essentially measures will be local correlators in the language of, I mean, if I take two faraway plaquettes and supposing I scale the distance to remain finite as I take the lattice spacing, I mean, I take that ratio such that it is a finite limit, then it would be effectively some kind of a gauge invariant correlator of local, a 2-point function of local operators, because the individual plaquettes are basically going to shrink to something like the local field strength at that lattice point. So those are the kind of correlators, I guess, that this gets a handle on, because as you were saying, if I want to compute a macroscopic Wilson loop, then that is not something we can easily access this way, right?
Because, well, I think as we discussed, you see, in the case of two-dimensional lattice, which I have not covered here, you'll have a certain number of plaquettes, and you'll have to add more loops to get a complete set, and among them there will be arbitrary large loops, and the formalism applies straight away. That is why I can easily check that the results of Gross-Witten are, because Gross-Witten do have an expression for, in fact, Spenta said that he also has a paper where this is done, where a large loop, how the Wilson loop behaves, and that I can recover in the case of 2 dimensions.
Right.
Now, as you saw in the case of 3 dimensions, there are no large loops. So if you ask me what is the expectation value, the symplectic expectation value of a large loop, I have no answer. But on the other hand, there is a so-called Tohoft loop, which I can write down the analog of that.
Right.
Not that I've done anything with that. I mean, now as to your more physics-oriented remark about local correlations, I don't quite understand. I repeat, what one is able to check is that you can actually compute. By the way, this is already, I think, somewhat interesting because nobody seems to have done this, is that for the Chern-Simons phase space, if you take n Wilson loops, what do the joint distributions look like? And that this formalism easily enables you to see. And it's a fact that for finite genus, these Wilson loops are correlated. But as the genus becomes large, the correlation between 2 loops disappears. And which is the case with the lattice. If you take lattice, I mean, this was implicit in what I said. I hope this, I didn't actually spell it out. The point is that if you take lattice Wilson loops, 2 disjoint Wilson loops are correlated, uncorrelated even for a finite lattice. Wilson loops around a cube obey some kind of relation, which is recovered here in the limit of large lattice, etc., etc. So beyond that, I really don't, except in terms of doing the math and checking that for the symplectic correlations, the correlations actually decay. Symplectic correlations of plaquettes in the symplectic expressions actually decay. If that happens, then it will be worthwhile to spend the effort to actually compare these correlations with the lattice gauge theory correlations, because whether they actually agree in the large thermodynamic limit or not, I mean, as I said, I have not even formulated precise conjectures.
I mean, the main, I think this accesses a certain set of, I think, gauge invariant correlators, which depend on individual holonomies of the microscopic plaquettes. But if I think purely in the language of the unitary matrices of the links links in the lattice, there is also the relative angular degree of freedom. I think at least in the physics language, the way one says, I mean, between the plaquette and one plaquette and a neighboring plaquette, there is the holonomy which characterizes the plaquette, which is the eigenvalue, but the relative angle between the two unitary holonomies, that angular degree of freedom, I think, is what one really needs to, if one wants like a big, for instance, a big Wilson loop. So that, I guess, is not something one can access by the by the character variety, I think.
Rajesh, you know, so think of the Gauss's law for a cube. I mean, there are the six the six holonomies. Surely they involve whatever you mean by angular relations, and the fact that the Gauss's law is reproduced by this integral, it is far from obvious. I mean, until you do the computation, you don't see it. And secondly, as I said, there are things you can write down which don't involve large Wilson loops, which have analogous expressions here, plaquette interaction correlations, for example.
No, that's why I was saying earlier, I think, and including Gauss's law, anything that includes the local field strength, and the Gauss law is ultimately a statement about the divergence-free nature of the non-abelian field strength. I think anything which involves the field strength, local field strength, is captured by a single plaquette variable and its holonomy. But the things which so those set of gauge invariant observables, I think probably the field strength.
So if you are saying that not every gauge invariant correlation in the lattice theory can be expressed like this, even or has a symplectic analog, I totally agree. But you know,
it's a large set of useful, I mean, because anything involving gauge fields, the field strengths and the derivatives, I think you definitely can access.
But on the other hand, modulo this conjecture or hope, if you can prove things for these correlation functions, you would have proved things for the corresponding correlation functions. That's a big if. I mean, both of these are ifs. You know, you have to first prove it for these correlation functions, and then you have to say that they are the same as for the lattice gauge theoretic correlation function. If you do that, but at least these expressions are interesting, and they are kind of, they're explicit. They're quite. I mean, there are no. You are not integrating over a large space of group valued variables. I mean, so there is some hope that these expressions can be analyzed with tools of statistical mechanics. I have no experience, or I don't know.
I was wondering, I've got a mic here, I think. Yeah, I was wondering if this is special to SU2. If you take SUN.
So I should have a better answer prepared for this. The point is, so I know an analogous thing in algebraic geometry where you can go to higher rank by, instead of you just take all invariant polynomials, and the numerology works out. So the question is, so there is a certain dimensional moduli space, and you want as many variables, as many functions as half the dimension of the moduli space to give a completely integrable system, action of S1, etc. I think if you take other invariant polynomials in the group, maybe with luck, the same thing will work. I have not thought about it.
And if you take SUN and let n go to infinity.
Sorry?
If you take SUN and let n go to infinity, large n limits, things might simplify in other ways.
Sure. Yeah, I know. So if yeah, absolutely. If the same picture held, there was an analogous picture for SUN, then one could combine this with a large N philosophy. And yeah, certainly, I really nothing to say. So I'm really sorry I didn't prepare that. I wanted to do some computation for you and show how that identity helps you actually compute things quite pleasantly, but I didn't prepare the computation, and I'm not good at doing things on foot. Yeah.
I have a question.
Yeah.
So you did this for the square or the cubic lattice, right? So suppose we try doing this for, say, the triangular lattice or the honeycomb lattice, even in D equal to 2. Does the choice of plaquettes, etc., become more complex?
Well, at least I formulated the thing in some generality.
Yeah.
And I told you where in D equal to 4, you run into a trouble because, what works so nicely in D equal to 2 and 3 is that the plaquettes can be lifted to the surface as mutually disjoint loops. You can find mutually disjoint loops which under the retraction map to the plaquettes that you are interested in. Already in D equal to 4 lattice, that is not possible. So I have to find ways of dealing with that. And if you have some honeycomb lattice or something, so perhaps the thing to do is to start with the other end, find the Pian's decomposition of the surface, project two closed loops on the lattice, and yeah, that might, yeah, I have no, yeah.
Thanks.
Okay, thanks. If Spenta is there, get well. And, yeah.
Thank you. Thank you very much. Thanks.
Okay, if there are no other questions, let's thank Professor Ramadas again for a very illuminating talk.
Can I take this out?